How close can three numbers get to a target of 1 when the best you can do is off by exactly 1? Today, let's look at a classic problem. 3 sum closest. Opening. We are given an array of integers and a target value. We need to choose any 3 numbers from the array and add them up, and we want that sum to be as close as possible to the target. The problem guarantees exactly one best answer, and we hand back the sum itself, not the distance. As an example, with the numbers -1, 2, 1, and -4, and a target of 1. The triple -1, 2, and 1 adds to 2, which is just 1 away from the target. So we give back 2. Naive approach. A direct solution is to check every possible group of 3 numbers. We nest 3 loops, 1 per chosen number, compute their sum, and keep track of whichever sum is closest to the target. This is simple and obviously correct. But with 3 nested loops, the running time grows with the cube of the array length. We can do far better by sorting first and then walking 2 pointers inward. Core idea. The key insight is that once the array is sorted, we can fix 1 number at a time and use 2 moving pointers to find the best partners to pair with it. We place the left pointer right after the fixed number and the right pointer at the far end. At each step, we add the 3 numbers. If the sum is exactly the target, we are done immediately, because nothing can be closer than a perfect match. If the sum is too small, we move the left pointer to the right to raise the sum. If the sum is too large, we move the right pointer to the left to lower it. Because the array is sorted, each pointer move is a deliberate step toward the target, so the inner sweep costs only linear time. With 1 outer loop over the fixed number, the whole algorithm is quadratic in n. Key details. 2 pruning tricks and a few details keep it tight. First, before the inner sweep, we check the smallest possible triple with this fixed number, which is the fixed number plus the 2 smallest remaining numbers. If that smallest triple already exceeds the target and is farther away than our current best, then every later fixed number will only be larger, so we can jump out of the outer loop entirely. Second, we check the largest possible triple, the fixed number plus the 2 largest remaining numbers. If that largest triple is still below the target and farther than our current best, this fixed number is too small to help, so we skip to the next one. Third, whenever a triple improves on our best, we record it and update the best distance. Fourth, if that best distance ever reaches 0, we have an exact match and hand back the answer right away. Fifth, after each pointer move, we skip over duplicate values so we do not retest the same triple. We also seed the best sum with the very first 3 numbers before the loop begins, so we always have a valid answer to compare against. Walkthrough. Let's trace the first example. We are given the numbers -1, 2, 1, and -4, and a target of 1. We will sort, fix each number in turn, and sweep 2 pointers inward to find the closest sum. We start by sorting the array. The 4 numbers become -4, -1, 1, and 2 in increasing order. Sorting lets the 2 pointers march inward and lets us reason about the smallest and largest possible. The triples. Next, we initialize the closest sum. We take the first 3 numbers, -4, -1, and 1, which add to -4. The distance from -4 to the target of 1 is 5. So our best sum starts at -4, and our best distance starts at 5. Now we fix the first number at index 0, which is -4. The inner loop will pick the other 2 numbers to go with it. Before sweeping, we run the first pruning check. The smallest triple we can form with this fixed number is -4 plus the next 2 smallest numbers, which is just -4 itself. That is not above the target, so the early exit condition does not trigger, and we keep going. We run the second pruning check. The largest triple we can form here is -4 plus the 2 biggest numbers, 1 and 2, which is -1. That is still below the target and not farther than our best distance, so we do not skip. We proceed to the 2-pointer sweep. We place the 2 pointers. The left pointer sits at index 1, the number -1, and the right pointer sits at index 3, the number 2. The fixed number stays at -4. We compute the first triple. -4 plus -1 plus 2 gives -3. The distance from -3 to the target of 1 is 4, which is better than our current best of 5. So we update the closest sum to -3, and the best distance drops to 4. We have a new leader. Since -3 is below the target, we move the left pointer to the right to raise the sum. It advances past -1 and lands at index 2, the number 1. We compute the next triple. -4 plus 1 plus 2 gives -1. The distance from -1 to the target is 2, which beats our best of 4. We update the closest sum to -1, and the best distance drops to 2. Another improvement. -1 is still below the target, so we move the left pointer again. It advances past 1 and lands at index 3, where it meets the right pointer. The two pointers have crossed, so the inner sweep of this fixed number ends. Now we move to the next fixed number at index 1, which is -1. The inner loop will search to find partners to go with it. We run the first pruning check again. The smallest triple here is -1 plus 1 plus 2, which is 2. That is above the target, but its distance of 1 is not greater than our best distance of 2, so the early exit does not trigger. We continue. We run the second pruning check. The largest triple here is the same, -1 plus 1 plus 2, which is 2. It is above the target, so the skip condition about being too small does not apply. We proceed to the sweep. We place the two pointers of this fixed number. The left pointer sits at index 2, the number 1, and the right pointer sits at index 3, the number 2. The fixed number is -1. We compute the triple. -1 plus 1 plus 2 gives 2. The distance from 2 to the target of 1 is 1, which beats our best of 2. We update the closest sum to 2, and the best distance drops to 1. This is our best result yet, but it is not an exact match, so we keep going. Since 2 is above the target, we move the right pointer to the left to lower the sum. It retreats past 2 and lands at index 2, where it meets the left pointer. The pointers have crossed, so the inner sweep ends. The outer loop has now tried every viable fixed number, and no exact match was found. We hand back the closest sum recorded, which is 2. That is exactly 1 away from the target, and it is the answer. Complexity. The running time is quadratic in n. Sorting costs linear arithmetic time, and the outer loop runs roughly n time stot, with each inner sweep costing at most linear time. So the total is dominated by the quadratic two-pointer work. The pruning and duplicate skipping reduce the constant factor, but do not change the worst case order. R. The extra space we use is constant, since we only store a handful of variables and the sort is done in place. Summary. 3 sum closest comes down to sorting, fixing one number, and sweeping 2 pointers inward. The ideas to remember are these. Sort first, so each pointer move is a deliberate step toward the target. Seed the best sum with the first 3 numbers. On an exact match, hand back the answer immediately. Use the smallest triple check to jump out of the whole outer loop when the fixed number is already too large, and the largest triple check to skip a fixed number that is too small. Skip duplicate values after each pointer move to avoid repeating work. Thank you all, and see you next time.